We're going to look at the general principles of the electrophilic aromatic substitution reaction. So right now I'm not going to use a specific electrophile, but we are going to talk about the principles involved here. So you're going to be talking about doing a substitution on an aromatic ring, and it really does help to draw a calculi structure so you can see all the electrons in the ring. There should be some sort of a group attached to the ring other than a hydrogen, although hydrogens are acceptable. You can just do this with a benzene. You can do this with more than one substituent as well. But you need to understand how that substituent or substituents influence the ring. The ring is going to act as your nucleophile. It's going to act as your electron source for whatever your electrophile is. And so it's important to have an idea as to what R is. Now, R could be a variety of things, and you can see these in the table in your notes or in your book. But there are two different types of groups. There are electron donating or electron withdrawing. Now, it's very easy to figure out if R is electron donating or withdrawing. The easiest way to figure this out, in my opinion, is to take a look at the atom directly attached to the ring and determine what its oxidation number is. Not its formal charge, but its oxidation number. If its oxidation number is negative or 0, it will be an electron donating group electron withdrawing group into the ring. And those tend to be very helpful. If you have, on the other hand, a group that has a positive oxidation number, it tends to be an electron withdrawing group, and these don't tend to help these reactions out very much. So R, if you're talking about an electron donating group, might be something like an OR group, where R is a hydrogen or some carbon chain. This could be an alcohol, it could be an ether, or an ester. It could also be maybe an amine or a derivative of an amino group. Okay, so oxygen and nitrogen both have lone pair electrons. They're both very good electron pair donors. They're not the only groups capable of being electron donating, though. You could also be talking about alkyl groups. For example, a methyl group or any length of carbon chain. They're not quite as good at the job, but they are electron donating groups. Also, one that is electron withdrawing, but still is classified as an electron donating group, would be your halogens, like fluorine, chlorine, bromine, and iodine. All of these tend to be orthopara directors when you do electrophilic aromatic substitution. And it's due to the fact that these atoms are electron withdrawing from the ring, electron donating into the ring and making it more negative, and therefore a better nucleophile for these types of reactions. If, on the other hand, you use an electron withdrawing group, you're talking about using something like a carbonyl carbon directly attached. So this could be an aldehyde or a ketone, or an ester where the carbonyl carbon is the one directly attached, not the oxygen. You could be using an acyl chloride. You could be using an amide where, again, the carbonyl carbon is the atom directly attached. Something along these lines. They tend to be very useful. A nitro group. In this case, that nitrogen does not have the lone pair. It actually has a formal charge of +1, and it has an even more positive oxidation number. So this is a very good electron withdrawing group. Also, you might be talking about a carbon with halogens attached to it. This is also a very good electron withdrawing group. But if you take the time to look at the oxidation number of any of these groups, you'll be able to figure out if the groups are electron donating and tend to be the orthopara directors, or electron withdrawing and tend to be the meta directors. And again, if you can figure out your oxidation numbers, you will know what to do and when to do it. So next up, let's actually take a look at the mechanism in general for any of these types of reactions. So we're not going to specify what R is, other than to say let's have R be an electron donating group. Sorry, electron withdrawing group. We'll do an electron withdrawing group, meaning that this is an orthopara director. So you would have an electrophile. Now, there has to be something else in solution, an anion associated with this cation. It doesn't matter what that is right now. But there has to be something that would have helped you generate this electrophile to begin with. So what happens is the ring is going to donate electrons to this electrophile. And as that occurs, you will add it to the ring. And due to the fact that we said that R was an electron donating group, you would add this group either ortho or para into the ring. It could be either one of these options. Now we're going to talk about drawing resonance structures here in a minute. So the positive charge must be maintained. You had a positive electrophile, you must maintain a positive charge. So the pair of electrons that was part of the aromatic ring has now made the bond to the electrophile. Now that positive charge that we now have can be delocalized through the ring via resonance. So we're going to show some resonance arrows. You can delocalize this guy all over the ring. Oops. Again, remember, if you are talking about resonance, you can only show resonance between electrons that are making double bonds or lone pair electrons. So the carbon in the ring that is now sp3 hybridized will never be involved in the resonance because it doesn't have a p orbital. But this positive charge does move through the ring. And there will always be 3 resonance structures through the ring. And these are the 3 that you would have. Now there may be a 4th resonance structure. It depends on what R is. If R is a hydrogen or an alkyl group, this is all you have. You only have the 3 resonance structures. But if R is an electronegative atom with lone pair electrons, like a nitrogen or an oxygen, you're going to get a 4th resonance structure. And I want to show you what that would look like. And it will come directly from this resonance structure here. So I'm going to show that one, going to a different one. So I'm going to redraw the one I had on that previous slide. Now, if R really does have a lone pair of electrons, what it does is it can actually donate this pair to this position. And as a result of that, you can get this 4th resonance structure, which shows the positive charge being actually delocalized off of the ring and onto whatever this electron donating group is. And that's the power of having those extra electrons. Now, if this were an electron withdrawing group, you would have been directing the group E into a meta position. And there would not be a 4th resonance structure like you're seeing here. This only occurs if you have an electron donating group, and if that electron donating group has a lone pair of electrons. So now that we have these resonance structures, I'm going to go back and just draw the one. But you can do this from any one of those resonance structures because, again, remember, resonance structures are telling you that you have charge delocalization. To completely describe what that intermediate looks like, you would need to truly draw all of its resonance structures. But I'm only going to draw the one right now. Okay, so once you're at this point, there should be some anion in solution that was associated with that electrophile to begin with. We'll call it Y. And it will be something that has lone pair electrons. I'm not saying it's going to have 4 pairs of lone pairs, but it's definitely going to have lone pairs. And what's going to happen here is it will come in, remove this proton, and as that happens, the carbon-hydrogen bond will break. And carbon, being the more electronegative of those two elements, will take those electrons and use them to make the carbon-carbon double bond. And again, remember, if this is an electron donating group into the ring, it not only forms this ortho product, it would also form the para product. It is going to form both of them. But this is where you'll end up at the end of the day.